Okay, good morning, everyone. I'm going to wait just a minute or two to see if anyone else joins, and then we'll get started. All right, I'm going to go ahead and start. Okay, last time we looked at amino acids and proteins, and we're going to survey some of the biochemical topics. The next one we're going to look at is lipids. And give me just a minute to share my screen. All right. All right, so this is chapter 19 in your textbook. All right, lipids are a heterogeneous class of naturally occurring organic compounds. In other words, they don't have structural commonalities. They're various classes, but what they do have in common, this is the main thing. They're insoluble in water. They're soluble in aprotic organic solvents, including diethyl ether, dichloromethane, and acetone. And these are some of the classes of lipids that we'll look at. These include triglycerides, phospholipids, prostaglandins, fat-soluble vitamins, cholesterol, steroid hormones, and bile acids. Okay, we'll start off by looking at triglycerides. These are fats or oils. Okay, so a triglyceride is formed when we start with glycerol, which is 1,2,3-propane triol, and we form esters at each one of the alcohols with these fatty acids. Okay, this is a reaction called saponification, which we'll talk about in just a moment, where we heat a fat or oil with sodium hydroxide. And we can stop at this first step depending on what we want to do. But in order to precipitate out the fatty acids, we would add HCl to that. Right, here's a space-filling model of a couple of different triglycerides. And red represents oxygen, white represents hydrogen, and this light green represents carbon. Right, this is what's called a saturated triglyceride or saturated fat, which means that in this particular molecule, there's no double bonds in the chain. Okay, notice that these fatty acids consist of long chains, long R groups. Okay, here is an unsaturated or polyunsaturated fatty acid. Okay, notice here that one or more of the side chains stick out sharply to the side. Okay, fatty acids. All right, fatty acids are what we get when we break down a triglyceride, or what is used to form a triglyceride. And these are the characteristics of most fatty acids. Nearly all have an even number of carbon atoms. Okay, most of them between 12 and 20, and the chains are unbranched. Okay, the reason that they contain an even number of carbon atoms is the chains are biosynthesized 2 carbons at a time from the acetate or acetyl group. Okay, the 3 most abundant are palmitic, okay, which has 16 carbons and no double bonds, stearic, which has 18 carbons and no double bonds, and oleic, which is 18 carbons and 1 double bond. Okay, in most unsaturated fatty acids, the cis configuration predominates. The trans configuration is rare. Okay, unsaturated fatty acids have lower melting points than their saturated counterparts. The greater the degree of unsaturation, that is, the more double bonds, the lower the melting point. All right, here are some representative fatty acids. These are found in natural products like animal fats, vegetable oils, biological membranes. Okay, so here are the saturated fatty acids, no double bonds, that's what the 0 indicates. And as we increase the number of carbon atoms, okay, we see that the melting point goes up. All right, so since room temperature is about 25 degrees, okay, that tells us that all of these are solids at room temperature. Okay, here are some unsaturated fatty acids. Okay, we have palmitoleic, oleic, linoleic, linolenic, and arachidonic, which actually has 4 double bonds, and you can see that all of those are liquids at room temperature. Right, so here are some bond line formulas for some of the fatty acids. Here's stearic, no double bonds. Stearic is a major component of beef fat, for example. Oleic has 1 double bond, and it's a cis double bond. Linoleic has 2 double bonds, they're both cis. Notice the first double bond occurs between carbons 9 and 10. Okay, the second one is not conjugated with the first one. There's a CH2 in here. And then linolenic has 3 cis double bonds. And none of them are conjugated. Right, the physical properties of the triglycerides depend on the fatty acid components. The melting point increases as the number of carbons in the hydrocarbon chains increases and the number of double bonds decreases. Triglycerides rich in unsaturated fatty acids are generally liquids at room temperature and are called oils. Triglycerides that are rich in saturated fatty acids are generally semi-solids or solids at room temperature and are called fats. Okay, one exception is palm oil and coconut oil, which come from plants, are highly saturated. They're both solids at room temperature, but they're still called oils. Okay, so here's the reason for the lower melting points of triglycerides rich in unsaturated fatty acids. Those are related to the differences in their 3-dimensional shape. Right. Hydrocarbon chains of saturated fatty acids can lie parallel with strong dispersion forces between their chains. They pack well and they pack into well-ordered compact crystalline forms and melt above room temperature. Okay, so let's go back a few slides here. Okay, so here's a saturated fat. Okay, the chains are relatively straight, and so several of these molecules can pack together side by side, and you have a lot of London dispersion interactions. Okay, because of the cis double bonds in the unsaturated fats, we'll have side chains that stick out sharply to the side. So that means that these don't pack together as well as the saturated fats do. And so the number of London dispersion forces, the area through which London dispersion forces can operate is much less. Okay, so saturated fatty acids can lie parallel. And then because of the cis configuration of the double bonds in unsaturated fatty acids, their hydrocarbon chains have a less ordered structure and dispersion forces between them is weaker. And these triglycerides will have melting points below room temperature. Okay, we're going to look at some of the reactions of triglycerides. Okay, one of the processes that involves converting oils to fats is called hardening and involves catalytic reduction of some or all of the carbon-carbon double bonds. Okay, this is, they use hydrogen and a catalyst. Okay, so the resulting fats are sold for cooking. So this is a way of converting oils into shortening, okay, such as Crisco, Spry, and others. Margarine and other butter substitutes are produced by partial hydrogenation of polyunsaturated oils derived from corn, peanuts, and soybeans. Okay, you want to use just the right amount of hydrogenation. If you get too much hydrogenation, then the shortening or margarine tends to be somewhat brittle. Not enough, and it tends to be really greasy. Okay, because catalytic hydrogenation is to some degree reversible, hardening or hydrogenation results in the isomerization of some cis fatty acids to trans fatty acids. Trans fatty acids are to be avoided as much as possible. It's suspected there's a considerable evidence that trans fatty acids are not healthy. Okay, the other place where you would find hydrogenated oils would be in some creamy peanut butters. Okay, so that's reduction of the double bonds. Okay, another reaction of triglycerides is this one called saponification. Saponification literally means soap making. Today, though, it is used to refer to the basic hydrolysis or splitting of any ester. Okay, so we start out with a triglyceride, and we use 3 equivalents of sodium hydroxide, and this is carried out at high temperature, and this is done in aqueous solution. The triglyceride starts out insoluble in water, but as the reaction proceeds, you get a cloudy mixture. Okay, the combination of these sodium salts of fatty acids are what we call soap. The byproduct is glycerol or glycerin. Soap making is a very ancient process. It's thought to be at least 3,000 or 4,000 years old. It was practiced by the Greeks and the Romans. And you can use a number of different types of triglycerides to make soap. If you start out with olive oil, then the resulting soap is called Castile soap. You can use corn oil and sunflower oil and just about any vegetable oil. You can also use various animal fats to make soap. One time we even tried fish oil. It worked, it made soap, but the soap smelled terrible. Okay, so how do soaps work? Soaps clean by acting as emulsifying agents. The long hydrophobic hydrocarbon chains of soaps are insoluble in water and tend to cluster in such a way as to minimize their contact with the water. The polar hydrophilic carboxylate groups remain in contact with the surrounding water molecules. Driven by these two forces, soap molecules spontaneously cluster into micelles. Micelles are spherical arrangements of organic molecules in water, clustered so that their hydrophobic parts are buried inside the sphere and their hydrophilic parts are on the surface of the sphere in contact with the water. Okay, so here's a diagram of a micelle. These micelles are actually very small. They may consist of only about 80 to 120 soap molecules. Okay, so here you have, these are the hydrophobic tails of the fatty acids. And at the end, we have this carboxylate with a negative charge. And then we have sodium ions surrounding this. The dirt or grease that the soap is being used to dissolve will be buried in the interior. And so this emulsifies the dirt or grease or fat stains and allows you to wash it away. Okay, I might point out that, okay, back earlier in this presentation, it showed taking the carboxylate salts and then adding acid to make the fatty acids. The fatty acids actually don't work all that well to emulsify grease because although the carboxylic acid group is polar at hydrogen bonds, it doesn't interact as strongly as these ionic heads would. And so the fatty acids are actually going to be insoluble even though they contain a polar group. A bar of soap is partially soluble in water. Think about how long a bar of soap lasts. Okay, if you have hard water, and hard water is water that contains high amounts of calcium and magnesium ions. Well water usually contains iron 3 ions as well. And what happens is that the sodium salts or sodium soaps do an exchange. The calcium replaces the sodium. Since calcium has a +2 charge, okay, it will bind with 2 of these carboxylates. And these calcium and magnesium and iron salts are insoluble. Okay, the sodium soaps are soluble in water as micelles, but then you'll have a precipitate that forms in hard water. This is what's known as soap scum. Okay, in the same column of the periodic table, okay, if we go below sodium, we have potassium. Potassium soaps are what are used in liquid or soft soaps. If we go the other direction, lithium soaps are very insoluble, and those are used in as automobile lubricating greases. Okay, so we've seen the structure of soaps. Let's look at synthetic detergents next. Synthetic detergents also have a long hydrocarbon tail, usually 12 to 20 carbons. They'll have a polar head group that does not form insoluble salts with calcium, magnesium, or iron. And the most widely used synthetic detergents are the linear alkyl benzene sulfonates. Okay, so this is a sulfonate group. And this is what's called an anionic detergent. Okay, these operate the same way as soap molecules do. They form micelles, they emulsify grease or dirt, but they don't precipitate in hard water. Okay, this is what you would typically find in laundry detergents, for example. Okay, some of the things that are also added to detergent preparations include foam stabilizers, bleaches, or optical brighteners. Phospholipids are the second most abundant group of naturally occurring lipids. They're found almost exclusively in plant and animal membranes, which typically consist of 40 to 50% phospholipids and 50 to 60% proteins. The most abundant phospholipids are derived from phosphatidic acid, which is glycerol esterified with 2 fatty acids and 1 phosphoric acid. Further esterification with a low molecular weight alcohol gives a phospholipid, and we'll see examples in just a moment. The 3 most abundant fatty acids in phosphatidic acids are palmitic, stearic, and oleic. Okay, so here's the glycerol group. Okay, with the triglyceride, you'd have 3 fatty acids. With a phosphatitate, okay, one of the fatty acids is replaced with phosphoric acid. And then for a phospholipid, we form a phosphate ester with some alcohol. Okay, these are the common alcohols that are found in phospholipids. This one is ethanolamine. Here is choline, serine, and inositol. Lecithins are phospholipids that are found in, for example, in eggs and in soybeans. And lecithins are used in food processing to emulsify such things as mayonnaise, okay, in order to keep it from separating out into layers. Okay, when placed in aqueous solution, phospholipids spontaneously form a lipid bilayer. The polar head groups lie on the surface, giving the bilayer an ionic coating. Nonpolar fatty acid hydrocarbon chains will lie buried within the bilayer. Right, this self-assembly is driven by 2 non-covalent forces. There are hydrophobic forces, which result when the nonpolar hydrocarbon chains cluster to exclude water molecules. And then we also have electrostatic interactions, which result when the polar head groups interact with water and other polar molecules in an aqueous environment. Okay, in the fluid mosaic model, a biological membrane consists of a phospholipid bilayer with proteins, carbohydrates, and other lipids embedded on the surface in the bilayer. The fluid signifies that the protein components of the membranes float in the bilayer and can move freely along the plane of the membrane. Mosaic signifies that the various components of the membrane exist side by side as discrete units rather than combining to form new molecules or ions. Okay, so this is a diagram of the fluid mosaic model of a biological membrane. Here's the lipid bilayer. There's the fatty acid chains here, the ionic coating, and then we have things like cholesterol, which gives some measure of rigidity to the membrane. We have glycolipids, oligosaccharides, and proteins and other molecules. Okay, next we'll look at steroids. Steroids consist of a group of plant and animal lipids that have this tetracyclic ring structure. Okay, 3 6-membered rings and a 5-membered ring in this arrangement. These are called the A, B, C, and D rings. These are the location numbers. Okay, usually the 6-membered rings are trans. And each atom or group at a ring juncture is axial. The pattern of atoms or groups along the ring junctions is nearly always trans, trans, trans. Okay, and what this does is makes the steroid system nearly flat and quite rigid. Most will have axial methyl groups at C10 and C13. Right, here is cholesterol. And we talked about stereocenters early on in the semester. And these stereocenters are all marked. There are 256 stereoisomers that are possible, but only this one is found in human metabolism, just this one stereoisomer. Cholesterol serves a number of purposes. It is used as a starting material to make other steroids. It is, as we saw just a few slides ago, it's found in cell membranes to give the right rigidity. Okay, these are the male sex hormones, testosterone and androsterone. These have the steroid structure. Okay, and these are responsible for the development of male secondary sex characteristics. Okay, there's one that's called dihydrotestosterone, okay, in which this double bond is reduced. And this is what's found in aging males, which causes hair loss and some other problems. Anabolic steroids will promote tissue and muscle growth and development. These are some examples. These are the female hormones. They're synthesized in the ovaries. We have progesterone and estrone. Progesterone-like analogs are used in oral contraceptives. This is This is ethinyl progesterone. Okay, it has this triple bond here, and it also has a hydrogen in place of the methyl group. These are glucocorticoid hormones. These are synthesized in the adrenal cortex. They regulate metabolism of carbohydrates, they decrease inflammation, and they are involved in the reaction to stress. Okay, so here's cortisone. Okay, one is the suffix for a ketone. This is cortisol. Okay, we have a ketone here and an alcohol here. And here's one that helps regulate blood pressure and volume by stimulating the kidneys to absorb sodium chloride and bicarbonate. Bile acids are synthesized in the liver, stored in the gallbladder, and secreted into the intestine. Cholic acid, okay, which is shown below, is an important constituent of human bile. Okay, and the function is to emulsify dietary fats and to aid in their absorption and digestion. Steroids are biosynthesized using a 2-carbon building block called acetyl coenzyme A. At least the acetyl part is 2 carbons, and then it's attached to a larger group called coenzyme A. Okay, the first step in the biosynthesis of steroids is the synthesis of isopentenyl pyrophosphate, okay, from 3 molecules of acetyl coenzyme A, and then cholesterol is synthesized, and then cholesterol is converted into other steroids. Okay, I'm going to skip over this part. All right, another class of lipids is called the prostaglandins. Okay, this family of compounds consists of a 5-membered ring, and their prostaglandins are 20 carbons. You have a 5-carbon ring, and then you have 2 long chains on adjacent carbons of the ring. These side chains can contain a variety of functional groups, alcohols, carboxylic acids, ketones, alkenes, and so on. Prostaglandins are actually not stored in the tissues as such. They're synthesized from this molecule called the arachidonic acid. And they are synthesized in response to specific physiological triggers. Okay, these are a couple of examples of prostaglandins. Okay, these letters indicate a number of different things, like the different functional groups, where the double bonds are located, and various things like that. Prostaglandins are extremely powerful regulators. It just takes a very small amount of prostaglandin to invoke a type of response. They perform a variety of different functions. This is, one is they stimulate uterine contractions. There are some that are involved in dilating or constricting blood vessels. There are some that are involved in relieving inflammation. There are some that cause inflammation. Okay, this is one that's used to prevent the ulceration associated with the use of aspirin-like non-steroidal anti-inflammatories. Okay, one of the ways that ibuprofen and aspirin work is they inhibit an enzyme called cyclooxygenase, or COX, and that prevents the formation of anti-inflammatory prostaglandins. Okay, here we have the eicosanoids. Again, these are all 20 carbons like the prostaglandins. They're derived from polyunsaturated fatty acids. This one is a vasoconstrictor. Leukotrienes are found primarily in white blood cells. One function is constriction of smooth muscles, especially those of the lungs. I'll mention briefly fat-soluble vitamins. Okay, these include vitamins A, D, E, and K. Right, here is beta-carotene. Beta-carotene is responsible for the orange color of pumpkins, sweet potatoes, and carrots. And in the liver, beta-carotene is cleaved to form retinol, which is vitamin A. Vitamin A plays an important role in vision. The active molecule is retinal, which is the aldehyde, that forms an imine. Okay, an imine, remember, that's a CN double bond. It forms an imine with a protein called opsin. And that gives us a visual pigment called rhodopsin. Okay, so the primary chemical event that occurs with rhodopsin is you have the cis retinal, 11 cis retinal, and when light strikes it, that causes isomerization. So this uncoils, it straightens out, and that sends a nerve impulse. Right, here is vitamin D. Okay, notice the similarity to the steroid structure. Here is vitamin E. The most important function of vitamin E is it serves as an antioxidant. Okay, and what that means is that oxygen will form free radicals, these species that have unpaired electrons. These free radicals will cause chain reactions. They'll generate more free radicals. And vitamin E serves to stop that process. Vitamin C is also a antioxidant, but it's water soluble. Okay, and here's vitamin K, which is involved in coagulation. All right, so for purposes of testing, let me just briefly go through here. If I show you a picture of a structure, okay, you should be able to tell me what class of lipid it belongs to, whether it's a phospholipid or a triglyceride or a steroid or prostaglandin. So I don't expect you to be able to name individual steroids, for example, or individual prostaglandins, but be able to recognize the class of compounds. Okay. Also, be familiar with the saponification reaction. Okay, be familiar with why unsaturated fats have lower melting points than saturated fats. Okay, know the difference between cis and trans fats. Be familiar with hydrogenation of fats. Understand how soaps and detergents work and how they form micelles. Okay, other than that, again, I would not ask you to draw the structure of lecithin or something like that. All right, so that is it for today, and I will see you on Monday.